So, hello, my dear friends. Today, in this video, we will be looking at the concept of electric dipoles. Electric dipoles are actually a system of two charges separated by a finite distance. So, let us first look into the definition of what an electric dipole is. So, there you have it. An electric dipole is a system of two charges whose magnitudes are equal but are opposite in polarity, separated by a finite distance. So, according to definition, an electric dipole is nothing but two similar magnitude charges, but charges with opposite polarity, separated by some finite distance. So, this could mean that one of these charges will be a plus q, an arbitrary plus q, and the other one will be an arbitrary minus q, where q, the magnitudes are same, but as you can see, they are of opposite polarities. The distance that separates them, the finite distance that separates them, is known as the dipole length of the electric dipole. If an electric dipole is considered as an system, the total charge of the electric dipole will be plus q minus q, which is 0 coulomb. So now let us look into some real life examples of an electric dipole. So as per the definition, we have a few examples which I want to state here. In fact, there are many examples that would come under the definition of an electric dipole, but the most familiar ones are being stated here. As a first example, I would like to put down water molecule. So water molecule is one of the best examples of an electric dipole. So water molecule is an electric dipole because, so let us see why a water molecule which is neutral overall is an example of an electric dipole. This happens because of the difference in electronegativity of the atoms involved. From your study of chemistry, you must know that oxygen is more electronegative as compared to the hydrogen atoms, which are themselves electropositive. So what happens is that the electrons, the outermost electrons, which is the one electron on each of the hydrogen atom, is drawn more towards the more electronegative oxygen atom, thus giving oxygen atom, not molecule, oxygen atom, an amount of minus 2 electric charge in excess, whereas each hydrogen molecule becomes plus one positively charged, In this situation, the plus one positively charged hydrogen atom on the left and the one on the right together have a center of charge exactly in between them, and the total charge of the two hydrogen atoms will be plus 2e, whereas that of the oxygen atom will be minus 2e. So as you can see, in this situation we have separation of center of charges, which is we have minus 2e on one side and we have plus 2e on the other side. So we have separation of charges which are equal in magnitude but are opposite in polarity by a very tiny distance between them. The dipole length between the separation of the center of charges of water molecule can be calculated. According to the website of ResearchGate, it is mentioned that the bond angle between the two hydrogen is approximately 104 degree, and the separation between a pair of oxygen and hydrogen is around approximately 0.1 nanometers. So if the distance between O and one of the H is 0.1 nanometer, then by bisecting the angle 104, we see that the separation between the center of charge plus minus 2e and plus 2e can be calculated using basic trigonometry, which is this angle would be exactly 52 degrees and this length will be 0.1 nanometer cos 52 degree. So the concept of dipole moment is crucial because it will be used to evaluate a very important physical quantity associated with electric dipoles. Not only just electric dipoles, but we can make use of the physical quantity and associate with any known electric charge system. Another best example for an electric dipole would be carbon monoxide molecule. The carbon monoxide molecule has one carbon and one oxygen atom covalently bonded by 3 bonds, and also in this case the electropositivity of carbon is greater as compared to the oxygen, which is oxygen molecule is more electronegative as compared to the carbon atom. Due to this difference in electronegativities, the electron from the carbon side is more drawn towards the oxygen atom, thus making oxygen atom or the region of the oxygen atom negatively charged and thus making the region of the carbon atom positively charged. Out of the 3 shared electrons from each atom, the 3 from the carbon atom is pulled towards the oxygen atom, thus making the region of carbon atom deficit of electrons, which causes it to become +3 electronic charge units, and the oxygen atom region becomes -3 electronic unit charges. So thus again we have separation of charge centers of equal magnitudes but of opposite polarities, and they are also separated by a tiny distance which is their dipole length. And according to National Institute of Standards and Technology, US, the dipole length, which is the separation between the two center of charges, is around 112.8 picometer, where pico is a suffix used to denote 10 raised to -12. So 1 in 10 raised to 12. So these two molecules, water molecule and carbon monoxide molecule, are two best common examples of an electric dipole. Now let us look into a few measurements associated with an electric dipole. So an ideal dipole would be two equal charges with opposite polarity separated by some finite distance, and the distance between the two centers of charges is called the dipole length, and the magnitude of charge in one of the center of charge is Q. So before defining any physical quantity associated with any electric dipole, we need to label a few things on this electric dipole. Since this is a system of two charges, I would like to introduce a coordinate system to measure the positions of each charge centers in the system with respect to some prefixed origin, where origin can be conveniently fixed by any observer. Now, introducing a coordinate system to make measurements around an electric dipole is useful because we may be able to associate other indirect physical quantities such as electric field, electric force, etc. due to the electric dipole in the space around it. So for that we need to fix some origin, conveniently of course, to measure the distance of any point in space with respect to the dipole. So let us introduce a coordinate system. For that I can mark an origin anywhere in this two-dimensional space. So let me just select this point O as our origin, which is the reference point, and let one of the charges of the electric dipole be plus Q and be located here, and let the position 2 plus Q from O be marked using a vector, and I will call it vector R1. Similarly, the negative charge center of the electric dipole could be somewhere around, which is the minus Q, and also distance to this particular charge or the position of this particular charge can also be measured from our convenient prefixed origin. I would call it R2, the position vector of minus Q with respect to O. Now we have already labeled these two charges with their position vectors. Now any other point in space can be marked using some other vector, another vector with respect to the origin. Let me call that particular vector as vector R. So it will describe some arbitrary point P in space around our electric dipole. So the first quantity that I would like to measure would be the total moment of charge of this electric dipole. The total moment of charge of any system is also known as dipole moment of the system. So how do you calculate the moment of charge? So moment is a quantity which contains a scalar multiplied with a distance measuring quantity. Now this could be the position, this could be square of the distance. So any of the quantity which is associated with a distance raised to some power can be multiplied with the scalar quantity, and this will give you the quantity, a quantity known as moment of that particular scalar. So moment of a scalar is just a product of that scalar quantity times distance or position vector or distance squared or distance cubed. So it can go on further as per the definition. In our case, we have the scalar quantity that we have is charge. So we are going to calculate the moment of each charge in the system and multiply it with the position vector in this case. So our moment of charge will look like some quantity mu, which will be a vector, of course, because we are scaling the position vector with the charge. So you are multiplying position vector with charge, so we will get a vector again, and this vector is the moment of that particular charge. So in this case we have two charges, so we can calculate two moments of charges, mu plus, which will be the moment of charge of the plus q charge, and that will be plus q times position vector of plus q, which is r1, and we have moment of charge of the negative charge, which is minus q times the position vector of the negative charge, which is r2. Now the total moment of charge will be the vector sum of each moment of charges, which is mu1, vector mu1 plus vector mu2. We can denote the total moment of charge using another symbol. I may call it a small p, and it is also a vector because you are adding two vectors, and the resultant will also be a vector. So as I told you earlier, total moment of charge of a system is also called dipole moment, and dipole moment is also a vector quantity. It's also a vector quantity, and you get it by adding the individual moment of charge of the system, which is given as mu1 and mu2. So what was mu1? Mu1 was plus q. In our case it is mu plus, and the other one was mu minus. So let me just rewrite it like that. And the position vectors are 1, and we have plus, then we have minus q times r2. So this will give you the dipole moment. Now as you know, the two charges have similar magnitudes, so that we can pull that q outside. So what's inside is vector r1 minus vector r2, where the minus belonged to the minus q and was left over inside the bracket. Thus you get the dipole moment of the system. So this is how you define the dipole moment of an electric dipole. Now the direction of the dipole moment P will be along the direction which is indicated by the difference of the two vectors r1 and r2. So we may just go ahead and look into what r1 minus r2 will be. So to find the difference vector r1 minus r2, let us look back into the figure that we drew a few moments ago. So the difference vector r1 minus r2 can be evaluated easily. The difference vector is actually the vector, the separation vector between the two charges. So this is your, so this will be your vector r1 minus r2, and the direction of r1 minus r2 is from minus q to plus q, which means the direction of the dipole moment is from minus q to plus q. So dipole moment, the vector quantity P is q times the separation vector r1 minus r2, and I can call the separation vector as some d vector d, so which will give our dipole moment a new look, and it will look like vector P is equal to charge q times the separation vector d. The separation vector d is actually the separation between the minus q and the plus q charge, and we already know the distance between plus q and the minus q charge center was called dipole length. Thus the separation vector d can be called dipole length vector, or dipole separation vector, if you may like it that way. Now the magnitude of the dipole length vector is nothing but the dipole length. So magnitude of the dipole length vector is the dipole length of the system of the electric dipole. Thus in this terms you may be able to evaluate the magnitude of dipole moment. Magnitude of dipole moment will be nothing but magnitude of the charge times magnitude of the dipole length vector, which is nothing but charge times the separation d. So electric dipole moment, the magnitude is nothing but charge times the magnitude of the charge on one of the charges times the dipole length of the electric dipole. So for most of the calculations, this individual quantity in its scalar form may be used, and that would be sufficient enough to perform most of the calculations. Vector notations are invoked only when necessary. Another convenient origin for the electric dipole would be at the center of the dipole, and we may call it our new origin. So instead of placing the origin anywhere else, we may just conveniently keep it in the middle of the dipole, and we may be able to easily measure the distances from this origin to the two separate charges. So we have some vector towards the negative charge. I can call it vector r minus, and I can call the position of the positive charge as R suffix plus, so R plus. Again, the dipole moment vector will be in the direction from negative charge to the positive charge. Now any other point in space can be measured from this origin. So any point in space, any arbitrary point in space can be measured from this origin, and I may call that vector R. So some random point M in space around the electric dipole has a position vector R with respect to the newly selected origin, and the newly selected origin is at the dipole center. For the sake of convenience, this new coordinate system is more suitable, and if we draw a Cartesian coordinate system with respect to this origin, we can have the minus q charge at some point A in the I cap direction, and the plus q at exactly the same distance A, but now in the minus I cap direction. So the position vectors of plus q and minus q will be R plus will be A minus A I cap, and R minus will be A I cap. The preference of direction and the units in which distances are measured are totally dependent on the observer, because they can choose whatever lengths, directions as per their convenience. Thus, measuring the dipole moment in this new system will be P is equal to Q times R plus, which will be minus A I cap, minus A I cap, thus giving you the value 2 minus 2 times A times Q times I cap. So this itself indicates that our dipole moment is minus 2A Q I cap, where the magnitude of the dipole moment is 2 times A times Q, and the direction of the magnitude is 2 times A times Q, and the direction of the dipole moment will be in the minus I cap direction, which is from our negative charge to the positive charge. So this new coordinate system also gives the same result, and also proves one thing, that as you can see, 2A is nothing but the dipole length, which proves the fact that dipole moment of an electric dipole is an observer independent quantity. So the physical quantity, one of the most important physical quantity associated with an electric dipole is its dipole moment, and all electric field measurements or electric potential measurements or any other sort of physical quantities associated with an electric dipole will depend on this electric dipole, and we may see the results we derive will depend on the dipole moment as well as the separation or the position vector r at which we are measuring that particular physical quantity. So one of the most important quantity that in this chapter we want to evaluate is the electric field due to an electric dipole in the space around it. So electric dipole generates an electric field around it with individual charges involved. So we will be analyzing the electric field. So the value of electric field around an electric dipole can be evaluated using the principle of superposition, because in an electric dipole the two charges involved are a plus q and a minus q. So according to the principle of superposition, the electric field at any point, say any arbitrary point P, so it can be any point in the space, will be the total electric field at the point P will be a vector sum of the electric field due to these individual charges. So what I want to say is that at point P we will have a total electric field, and this total electric field will be the result of the sum of electric fields, the vector sum of electric fields due to the positive charge q and the electric field due to the negative charge minus q. So this is the fact that we are going to make use of and analyze the electric field at any arbitrary point. But the fact is, to evaluate electric field at any arbitrary point, it will take in-depth knowledge of coordinate systems, various coordinate systems, as well as one must be well versed with basic vector algebra. Thus, to avoid any complications, CBSE has instructed to find out the electric field in two regions of particular interest, where the evaluation of electric field is very easy as compared to at any other general point. Further study of electric field at any general point will require these two knowledge a priori to analyzing the electric fields. So we will be restricting our study only in the case of two particular regions. The regions involved are called the equatorial plane and the dipole axis. So we will be determining the electric field at any point on these two regions. So before going into further discussion, let me introduce to you briefly what these individual regions are and where they are located. So let us go ahead and get ourselves used to these two different regions around an electric dipole. So let us first look into our dipole axis, where this region is and what are the points that make up a dipole axis are. Actually, this is an imaginary line. This dipole axis is an imaginary line, in fact, an imaginary line that connects between that actually connects the two dipole charges, or an imaginary line that passes through two of the charges and extends up to infinity on either end. So this line is your dipole axis. So the points on this axis will be our points of interest, at which we will be finding the electric field, the total electric field due to this dipole. So any arbitrary point, so the electric field that we find for this particular case will be valid for any particular point, any arbitrary point on this axis, this line. So whether it be in between the two charges, or on the side of the positive charge, or even be it on the side of the negative charge, the equation for electric field that we generate will be valid. And so we will be looking at an approximation when this arbitrary point is very far away from the dipole center. So that will also be our case of study. So let us move on and get introduced to the equatorial plane. Equatorial plane, as the name suggests, is a two-dimensional plane surface. It's also an imaginary plane surface that is located in between the two charges of the dipole. So if you have the plus q and the minus q, it's this two-dimensional plane which is infinite. So the two-dimensional plane surface, which is the equatorial plane, lies between the two charges, and it is a pretty bit imaginative to take up to make an idea about this two-dimensional equatorial plane. For that, I have a study aid which I will be showing you right now. So as you can see here, we have two charges separated by some finite distance. I can show you this figure in 3 dimensions. As you can see, these are two charge particles separated by, I can change the separation distance between them. As you can see from the top, see now they are being more separated, so this is bringing them closer together. So this distance plays a very major role in determining the property of the entire electric dipole itself. So let us see what now you might know what a dipole axis is. It's an imaginary line that extends from one side infinity to the other side infinity. So it passes through both the charges together. There is only one line that does that, and that line is called the dipole axis. It goes through this charge and comes out through this charge over here. So let me show you what the the equatorial plane looks like, how the equatorial plane looks like. Do not mind the remaining box like structure which is around the electric dipole. It's just something associated with the simulation software. Alright, so let me show you the correct view of this equatorial plane. So this plane is actually not the equatorial plane. It is actually the plane that contains the two charges. So this is I can call it the plane, the charge plane, but this is not the dipole, the equatorial plane. The equatorial plane is actually perpendicular to this this structure itself. So let me show you the equatorial plane. Yeah, there you go. This plane is the equatorial plane. Actually, this is the equatorial plane. I hope you can see the equatorial plane over here. Yeah, over this side, this one is the positive charge. This one on the left is the positive charge, and this one on the right we have the negative charge. Don't mind the white dot in between. I think I can bring in more white dots just to show you a collection of points on this plane. So as you can see, those white points are the collection of points on this equatorial plane. So as you can see, this plane goes exactly between these two charges. So it passes through the center of the dipole, and also it is perpendicular to the axis, right? The axis which connects the two charges, the dipole axis which connects the two charges, should pass through this plane. And I can make it more distinct. Now we have the equatorial plane is much more visible. Let me just zoom out and show you, so that your imagination may catch in more idea. So I hope this makes clear what an equatorial plane is. This is the equatorial plane. Okay, this is the equatorial plane. So let me just take a screenshot of this. Should I take a screenshot of this? Yeah, maybe I can take the screenshot of this plane. Will that help? Let us see, will that help or not. I may add it in our board. So let me just copy it from here and keep that aside. So let me try to draw the equatorial plane in this figure. Yeah, which seems to be a humongous task, but still I'll try my best. If I had a 3D, I do have a 3D software, but right now I am not very energetic enough to draw that for you guys. So let me just adjust with this 2 dimensions. So there is your dipole center. So this plane is actually going like this. So this is the plane. Let me shade it. Let me just make it completely colored with this. Yep, so this will be the plane. See, there is no boundary to this plane. In fact, we are drawing a boundary just to showcase that it's a plane, it's a flat plane. It is actually a region which is infinitely wide and tall. So it extends to all direction. It's infinite. So there are infinite number of points. It extends to all directions. So This is what it looks like when you view it from one of the sides. Okay, so maybe you are viewing it from from the positive side, and yeah, we are restricted by the fact that we cannot draw a three-dimensional figure on a two-dimensional plane. But anyways, let me just try to paste the image that I copied. Oops, that's a very big image over there. Yeah, now I hope you can see. Let me represent the axis on this figure. The dipole axis on this figure would look like somewhat like this. Yep. Okay. So the two. So once again, just let me show it as if it is going through the center. So let me just cover this, whiten this part up. So now it really feels three-dimensional, right? Meanwhile, I would only suggest you to adjust with the low quality image, but this would be enough. Look carefully. The line is perpendicular to the plane, right? The dipole axis. So this is the dipole axis. We have our dipole axis, and we have the equatorial plane. Both are infinite in size. Equatorial plane. So we have both the figure now represented in the same image. Let me just reshade it with a different. Okay, fine. So there you go. You have your complete image represented. The point, these two geometrical objects, which is the dipole axis and the equatorial plane, actually pass through the dipole center O. So dipole center O is a common point. O is common point to both the geometric figures, which is the equatorial plane EP and the dipole axis DA. I am writing it in short just in order to save space and time. Now, I hope you may be used to the two figures, the two geometric figures that I have drawn around the dipole. This was, let me also mark one more thing in addition to whatever we were drawing right now. This is your plus q, this is your minus q, this is plus q, and this is your minus q. So that's it. This completes the entire figure. So now let us move on to calculation of the electric field, evaluation of the electric field. Remember, electric field is a vector quantity. So whatever calculations involved ahead will consist of using concepts from vector. So the major concepts that we are going to use is vector addition. So you need to be well versed with the concept of vector addition, as well as finding the magnitude as well as direction. Actually, what vector addition involves is finding direction of the resultant vector. So that's so the final total electric field is the resultant vector here, and also it involves the magnitude, determining the magnitude of E, so of the vector that we are going to find out. So whoever is not well versed with these two concepts may go and learn that first and then come back to view it from here on. So since you have come this far, let me tell you one thing. I'm going to represent the figures in a manner such that it looks you are going to view it from one side and you are looking at it from the exact center, which means you will be like some viewer sitting outside the electric dipole and you are one point in the equatorial plane. So I hope you understand that. Let me repeat. These are the two charges. This one is plus q, this one will be your minus q. Okay. Let me draw the dipole axis. So this is your dipole axis. I think that's too thick, so let me make it a bit thinner. Yeah, that would suffice. So you have your negative charge, you have your positive charge. Very good. And this is your dipole center. I hope that's the center. Let me just draw it a bit more close to the center. So this is your dipole center. I'll call it O. So this is your dipole axis. All right, so let us mark the distances of the two charges from the dipole center. The distance of our plus q from O is A, as well as the distance of minus q is also A, but in either directions. Suppose this is the x-axis. If this is your dipole axis is the x-axis, then minus q is situated towards the I cap direction, and plus q is situated towards the minus I cap direction. That's all. Well, we won't be invoking the vector form of dipole moment now. So for that case, we will be discussing it a bit later. So meanwhile, anyhow, let us move on. Since I have drawn the dipole axis, what will the equatorial plane look like in this figure? So the equatorial plane in this figure will look like a line. It will look like a line. So there you go. That's what I was talking about. You are viewing it from the plane itself. Okay, you are viewing it from the exact equatorial plane. One point, you are outside, you are not at O, you are somewhere else. So you are viewing it from that perspective, and that is why your plane appears to look like a thin line. Okay, a thin means zero thin. Okay, so this is your, I hope you can wrap around your heads with these concepts. Equatorial plane. Very good. This is your dipole axis. So any point on the dipole axis will be called a axial point. Okay, so any point on the dipole axis will be called an axial point, and any point on this equatorial plane will be called an equatorial point. So equatorial point. So remember one thing, the equatorial point. So equatorial point, what is the peculiarity? How would you even define the equatorial plane? See, there is one mathematical way to define equatorial plane. It is actually all the points that are equidistant from both the charges. So you can generate the equatorial plane mathematically by stating the fact that it is set of all the points x, not xy. If this is x-axis, then this will be then this will be the y-axis in the upward direction, and towards your direction, which is piercing out of the screen, you will have your z axis. So it is piercing towards you. Imagine as if it is piercing towards you. So the plane is actually zy plane. Your equatorial plane is zy plane. I hope you understand. The screen is xy plane, and your equatorial plane will be ZY plane. Imagine that. It's all up to you. I'm not going into any further discussion about various planes. So ZY plane. So ZY plane. So all the points on the equatorial plane will be Z and Y points, and a point in this plane, an arbitrary point P, any arbitrary point P in this plane can be denoted by Z and Y coordinates. So how do you define these coordinates? Actually, these coordinates are actually any coordinate, any point on this plane will be a point which is at an equal distance away from both plus q and minus q. Okay, it's easily demonstrable because see the center, for example, our central point or the dipole center is a point on the equatorial plane. So the distance of the central point from plus q is a, as well as the distance of minus q from this point is also a. So they are at the same distance, right? So it is very clear that any point on this plane is actually the same distance. Suppose this distance is r plus, and to this point I'm going to call it m, and the distance from here to here, let me call it r minus, but I mean this point m. Okay, but r plus is equal to r minus. The magnitudes, the distances are same. So that's how you can mathematically generate an equatorial plane. That was some kind of an additional information. So let us move on further. First we will be evaluating electric field at an arbitrary axial point. Let me call the arbitrary axial point as P. It could be anywhere beyond minus q, it can be anywhere between plus q and minus q, or it can be anywhere beyond plus q. So it is just any arbitrary point on the dipole axis, but I will be separately showing you these three regions because the direction of electric field is different in these three different regions. So just for that sake I will be showing you, but the magnitude of the electric field will be governed by the same equation which I will be showing you a bit later. So we are going to evaluate electric field on a point in the dipole axis. So remember, this will be our discussion. So let me get rid of the rest. First let me evaluate the direction of the electric field. So direction of the electric field is the first, the direction of the total electric field will be our first focus, and then we will move on to the evaluating magnitude of the electric field. Alright, so suppose I consider the first region, which is region beyond the plus q charge. So consider an axial point in a region. I will call it region 1, and that region is beyond the plus q. So this arbitrary point P will be our point of interest, where we are going to determine the electric field value and direction at that particular point. So when viewing it from this perspective, see, let me just get rid of everything else. Let me just label everything a bit later. So let that go, let the center go, everything go. Not that one, but let that go, everything else Go. We don't need you now. So this brings us to the basic figure or the basic question. What is the electric field at point P due to 2-point charges? That's the question. So that's what we end up asking ourselves, which will also give the answer to our ultimate question about the electric field on a axial point. So this case is something that we know already, because it's the situation where we invoke the concept of principle of superposition. So you have your plus q here. So let me label the distances. Let the distance, before labeling the distance, you could either just label it directly from the plus q like this and call it r plus, and also you can label it from minus q. Let me take a parallel here and then whoops, I'm very bad at drawing lines, so let me just make use of one of these tools. Yep, there approximately you go. It's a little bit bent, so it is a little bit bent. Let me just correct it. Yep, that takes us to the point P. See, this is the point P. Okay, remember this is the point P, the green marked one. And let me call this distance r minus. So the electric field at this point, what will be the direction of the electric field? Let us just look at. One thing is clear, that on the region 1, which was region beyond the plus q, any point is more closer to the positive charge. So any point in region 1 is more closer to the positive charge than it is to the negative charge, which means the electric field, the magnitude of the electric field at plus q will be greater than the magnitude of the electric field due to the minus q, because it is far away from the so-called point P in the region 1. So whenever you are representing it with a vector, when you are representing it with some vector, remember to have the vector due to the positive charge, the electric field vector due to the positive charge, to be larger in comparison to the electric field due to the negative charge. So if green arrow represents the electric field due to positive charge, so let me label or let me also color the green charge as, positive charge as green. So as you can see, it is easy for you to identify which vector is associated with which charge. And let me mark the red minus q with red color. So electric field which is red in color will be due to minus q. Okay, let me just draw that too, and there you go. See, the sizes should be different, which is due to minus q, it should be less. So there you go. There you have the electric field. See, the directions of electric field, I don't have to mention it, because due to minus q it will be towards the charge, and due to plus q it will be away from the charge. So this is your E plus vector E plus, and this will be your vector E minus. Okay, so you have E plus and you have E minus, not confused at all. Both are along the dipole axis. So both are along the dipole axis, and one thing is clear, that they are anti-parallel, which is the angle between them is 180 degree. They are collinear vectors. They are 180 degrees pointing opposite in direction. That means the total electric field at P will be easy for us to evaluate, because it is nothing but the total electric field will be nothing but the magnitude of the total electric field will be just the difference of the larger vector, which is the E plus, magnitude of E plus minus magnitude of E minus. So you have to just subtract the length of the two vectors. So subtracting length of the two vectors, you will have to get rid of this much from this. So you'll have to get rid of this much of the vector. Let me just draw that and erase it later. So I'll have to remove that much from the E plus. So I'm getting rid of that much vector. Whoops, I'm so sorry. I should have used another eraser. Yeah. So I'm removing that much of vector from E plus. So the remaining vector will be the resultant vector. Now this, my fellows, is the resultant vector. So the direction is given by the fact that the electric field will be, the total electric field will be pointed towards the larger arrow. In this case it was E plus, so the net electric field E must be pointed towards the E plus direction. So there you go, getting rid of all the rest of the remaining labels. You can see the direction is too simple now. So that's it. There you go. That's your that's your electric field, direction of electric field at region 1. Now what about the magnitude of E? The magnitude of the resultant vector is already given here. It's just the difference between the magnitudes of the individual electric fields due to the plus and minus charge. See, in this case the electric field is in the minus I cap direction. Remember that, keep this in mind, okay, because according to our label this is minus I cap. Okay, see, this need not be always the case, because it is only according to our convention. If the question paper gives and asks you something else, you should mark it accordingly. So our label is, this direction is minus I cap and this direction is plus I cap. Remember that. And this is plus j cap, and downwards is minus j cap, and towards you is plus k cap, and into the screen is minus k cap. So remember all those. I know this is getting a bit complicated, but don't worry. If you repeatedly watch this lecture, you will get the feel of it. Anyhow, let me evaluate the magnitudes. So first let me evaluate what is the magnitude or the electric field magnitude due to the plus charge in the dipole. For that you need to know two things. One is constant is already set to 1 by 4 pi epsilon 0, because we are evaluating everything in vacuum. All right. You have plus q divided by the distance r plus squared. So what is the distance r plus? So this is where we invoke our coordinate system. Now the point P, as I told you earlier, is some arbitrary point in the space around the dipole. So any arbitrary point around the dipole was represented using some vector r. Okay, and so the distance from O to P, so distance OP, distance OP is magnitude of that vector. Meanwhile, let me call it r. Okay, so that distance is r from here to here. Okay, so what is r, vector r then? Vector r is actually the position of the point P with respect to the origin. That's all. We already know the distance of vector of plus q. It's a. And we also know the distance of minus q from O, which is also A. I think this is enough to calculate the distance from O to plus Q and from O to, sorry, from P, not from O to P or O to plus Q, but from P to plus Q and P to minus Q. So these two distances were R plus and R minus, and it's very easy to find them out using R and A. Tell me, just imagine in your own mind and tell me what will the distance, the blue distance, the distance marked using the blue strip will be. You already know the distance from O to P, that is R, and you know the distance from O till plus Q. So the remaining distance will be the blue strip or the R plus, right? So R plus, let me call it R plus. So what is R plus? R plus is actually the difference of R and A, right? You just have to subtract A from R. R is this much distance from O to P, and A is just from O to plus Q. That means the remaining portion P to plus Q, which is R plus, will be nothing but the difference between R and A. So that part is clear. So you know R plus. Then what is R minus? R minus was this blue strip, right? Not the blue strip, but the somewhat pink colored strip. Okay, R minus. What is R minus? So to cover R minus, you know, you will have to add the distance from OP to the extra distance towards minus Q, which is A. So R minus, the total distance R minus is actually the distance from O to P to O plus the additional distance from O to minus Q, which is A. So there you go. You know the distances R plus and R minus. Very easy. Very easy. If you are confused a little bit, let me just erase all these and give you some sense of what it looks like a bit more clearly. So now you can look into this figure, which is actually rid of all those other labels. So R plus is, so before doing that, P, the point P is at a distance R from O. Okay, that's clear. Now the distance of plus Q from O is A. So you don't have to travel the entire R from plus Q. You'll have from plus Q, you can get rid of about A to reach P. So from this figure, anybody who is not confused will know that R plus in this case is R minus A. So that's there. Now what about R minus? R minus is the distance from minus Q to P. To reach P from minus Q, you'll have to first travel a distance of about A from minus Q to O, and from there we'll have to travel a distance of about R to P. So the total distance R minus is nothing but R plus A. So that's all. So now you have an idea about the distances from each charges. So electric fields, E plus, the magnitude E plus is 1 by 4 pi epsilon 0 times Q divided by R plus squared, and the electric field E minus is equal to 1 by 4 pi epsilon 0 minus Q divided by R minus squared. Or in this case you do not need a minus here, because the minus will have been taken care by the unit vectors already involved. So these are just magnitudes, so you do not need the minus here. It's just because they are magnitudes, they are not in the vector form, so I do not need the minus over there. And I had already mentioned earlier that the value of electric field, the total electric field E, the magnitude of E at P will be nothing but the difference of the magnitudes E plus and E minus. Subtract them and you will get the answer. And the answer to this is, if you perform your basic manipulations, you will know that it is 1 by Q by 4 pi epsilon 0 taken common out divided by 1 by R plus squared minus 1 by R minus squared. Okay, so this doesn't stop here. You know, we have a substitution for R plus already, and we also have a substitution for R minus in terms of R and A. So let us do the substitution. So writing down the electric field, the total electric field, the magnitude of the total electric field is equal to 1 by 4 pi, sorry, Q by 4 pi epsilon 0, taking it common out already. We had 1 by R plus squared. So what was R plus? It is nothing but R plus A the whole square minus 1 by R minus A. Actually, I'm sorry, I should have reversed them, because you know it is the opposite. Now I am correct. Okay. So after doing some basic mathematical steps, which is taking the adding these fractions, after taking the LCM, we will end up having this expression. So if anybody is confused, please go ahead to directly perform the calculation and check whether you arrive at this step. So you can pause the video and do that, and then if you are satisfied, then come back. Now let me move on with one more step ahead, which is I'm going to open these brackets, square brackets here, will result in this expression in the numerator. The denominator and the constant outside has not been changed, only these square brackets were opened. And while opening, I had also brought this minus sign into the brackets, so that's why we get this expression where minus R square is distributed. I mean minus is distributed over R square, and there was a minus 2AR, which with the additional minus becomes positive and A square becomes negative. So from this expression, as you can see, the terms that we can cancel out are the R square and minus R square. Then A square gets cancelled with minus A square. So the only two remaining terms are the 2AR plus 2AR. So in numerator, you add the two terms 2AR plus 2AR, and you get 4AR divided by R plus A the whole square into R minus A the whole square. Now let us manipulate the denominator. In the denominator, we have something like A raised to M times B raised to M. You have different bases but same power multiplied. For this case, we can just do the following. You multiply the bases and pull out the power as a common to both these bases. So it's like this is one of the basic rules of exponents, which is a raised to m times b raised to m will give you ab the whole raised to m. So in that sense, the denominator will become r minus a times r plus a the whole square. So the terms involved in the bracket look like a minus b into a plus b, which was equal to a square minus b square. So in that sense, the term in the numerator will further become easier to simplify, could be simplified into r square minus a square the whole square. The whole square was already there, so the only new thing was the r square minus a square inside the bracket. Okay, so we end up with this expression. See, there is nothing more to simplify in this apart from invoking approximations, which we will do in a moment. So before that, I can also write it down in the vector form. So as we know, the total electric field in region 1 was towards the minus I cap direction. So by knowing this, we can state the vector electric field, the total electric field in its vector form will look like Q. In the numerator we have Q times 4 times A times R the whole divided by 4 pi epsilon 0, and in the denominator we have this extra term r square minus a square the whole raised to 2, and the direction is let me put the minus sign here, minus I cap. Okay, so you know this. Now just by manipulating the numerator a little bit, a tiny bit, you can rewrite the numerator as minus 2 times q time 2 times a times q times r times I cap, and there is one more 2 also, which I can write it over here. So what I've done is I have just factorized 4 into 2 into 2. That's all. That's just, you will know why. In a moment. And in the denominator you have 4 pi epsilon 0 r square minus a square the whole raised to 2. That's all. So the purpose of splitting or factorizing this 4 was to identify the minus 2aq I cap as the dipole moment vector. So the dipole moment vector is your minus 2aq I cap. If you remember, I had already derived the dipole moment for our system and it was minus 2aq I cap. So rewriting it, the equation for electric field in terms of the dipole moment, this will look like minus vector p times r the whole divided by 4 pi epsilon 0 r square minus a square the whole raised to 2. So this is the expression for electric field at any point on the dipole axis, but actually this is in particular true for the region 1. So this is the region 1 of the dipole axis. So this is the region 1 of the dipole axis. Oh, there is one more correction here. I don't need this minus sign, right? I think I don't need that minus sign because I had already absorbed the minus sign in the expression here. So putting that was a big mistake. I'm so sorry. I made that mistake. That correction, I have done it now. Please remember there is no minus sign here in the region 1 case. So the direction of electric field will switch from region 1 to region 2 to region 3. That will be the only difference, but the magnitude of the electric field will be the same. So what will be the magnitude of the electric field? Magnitude of the electric field will be E, magnitude of the dipole moment P, times the distance R, the whole divided by 4 pi epsilon 0. In the bracket we have the distance again, R squared minus half of the dipole length A squared, the whole squared. So this will be the electric field at any point. This will be the magnitude of the electric field at any point on the dipole axis, at any axial point, at any axial point, whether it be in the region 1 or region 2, the magnitude will remain the same. I mean, it will depend on R by obviously. It will depend on R obviously. The expression will remain the same at any axial point, whether it be in region 1, region 2, or even in region 3. This is 3. So your derivation ends here with one more additional step which also has to be mentioned, and that additional step is actually making an approximation. So we are going to perform an approximation. So what is the approximation going to do? The approximation here that we are going to make is that we are going to assume the electric dipole is a very small dipole. We have a very small dipole, and the point the point P at which we are going to evaluate the electric field is very far away from the dipole center. Like, it's very far away, that the distance R in comparison to the half of the dipole length A, which is a very tiny distance, now the distance R is much greater than A. So you are evaluating the electric field. This approximation says when you are evaluating the electric field at a very far axial point, the expression for electric field reduces to, let us see what does it reduces into. The expression, the original expression was E is equal to 1 by 4 pi epsilon 0 P. I am only writing the magnitude. Dipole moment P times R divided by R square minus A square, the whole square. So while making this approximation, you can see this, if R itself is very larger as compared to A, then R square will be much larger than A square. So from here it would be like R square could be like some 10,000, whereas A could be some A square could be some 0.1. So when you add them together, the effect will be approximately equal to the larger number. which means you won't be worrying about the smaller part, right? This part does not matters to you anymore. So that's one thing. So this doesn't matters to you. So the only part that matters would be the larger part, which is the r square. So you can easily neglect the a square in the denominator, just like you did with the point 1. So you want to neglect a square from the denominator, and the expression you would get is, in the denominator, instead of r square minus a square the whole square, you neglect a square, and the answer will be r square the whole square, which is going to be r raised to 4. But now fortunately enough for you, as you can see, there is already one r in the numerator. We can easily get rid of one r from the denominator, thus resulting in the following equation, which is this. The equation will be, I'm not writing vector, so I don't want that. E is equal to 1 by 4 pi epsilon 0 times P divided by R cube. So if only if the point P is very far away from your dipole, which in most cases is true because the molecules you consider is very small, so this expression becomes very valid. So this is an approximate expression where the original expression is this, and after you did an approximation like this, you ended up getting this new expression where electric field is now only dependent on the dipole moment as well as the distance from the dipole moment, nothing more. Not, yeah, it obviously a is involved, but not in this complicated sense. See, in this case there is this complication of having a square in the denominator, and yeah, it's kind of bulky. But this one looks more beautiful, right? So let me just, to make it more beautiful, let me color this expression differently. Like I can put green, which means, yeah, good to go. So there you go. This is the final expression. So this is the electric field at any axial point due to an electric dipole. Now about the directions in the other regions, let me just evaluate that too. In region 1, you already know the direction of the electric field is, the total electric field is in the direction in the minus I cap direction in our sense. Okay, it's outward, away from the dipole center over here. Now what is the direction of electric field in the region 2? Region 2 is the region between the plus q and the minus q. So an easy contender would be the point O. At point O, the direction of the electric field will be, see, due to plus q, the direction of the electric field will be obviously in this direction. Okay, excuse me. And the direction of electric field due to the minus q will also be in the same direction, and well, obviously the size will be same. Why would the size be same? Because they are all at the same distance. Both the charges are at the same distance, and only the so the magnitude of the electric field due to the both the charges will be same. So which means they will add up, giving a net electric field towards minus q. So remember one thing, we forgot to mention that the direction of dipole moment, which should be dipole moment should be from minus q to plus q. So remember this. So in relation with dipole moment, the electric field in the region 1 is parallel, and in relation to the dipole moment, the electric field in the region 2 is anti-parallel. So there is the electric field in the center is actually points exactly opposite to the dipole moment vector. What about the third region? The third region will be our the region beyond the minus q charge. So any point in this region is more closer to the minus q charge than it is to the plus q charge. So what happens is that the effect of electric field due to minus q will be sufficiently larger. So sufficiently larger, let me label it red. So the electric field at point in the region 3 is larger and is due to minus q, so it will be a vector which is larger in pointing towards minus q, and that due to the plus q will be much less because it is farther away, right? So as we did in the region 1, we will get rid of this much of the effect from this vector, ending up in a vector which is shorter but still which points in this particular direction, which is towards the minus q. So let me just color it. The total electric field is now it's pointing towards this dipole center, and also it is parallel. As you can see, it is parallel to the p vector dipole moment. Okay, so that's it, guys. That's what we understand here. So remember one thing: on a far away point from the dipole center, the electric field varies as 1 by r cube. So this is one good example where electric field looks like not r square or not r, but instead it looks like 1 over r cube. So electric field is inversely proportional to the cube of the distance from the dipole center. Next section will be the discussion on equatorial point. That will be right now. So guys, let us now derive the expression for electric field due to an electric dipole at an equatorial point. For this, I am going to assume the figure in which I look from one of the sides. So the view looks as if you are viewing the plane dissectionally, so you would see it as a straight line. Now as you can see, we had already labeled this direction to be I cap, this direction to be minus I cap, and the vertical direction to be j cap, and the lower direction to be minus j cap. So this red colored plane, which is actually the zy plane or yz plane, whichever you're comfortable with, you can call, is the equatorial plane. It's the equatorial plane. Now you might question, how would it look like from some other angle? So it would look like this. Just look. If you are viewing that plane from the positive charge side, your positive charge might be here. Let me just extend the plane size so that it appears as if it's the positive charge is in front of the plane, and this will be the axis. This will be the axis. It will go through there, and your negative charge will be sitting behind it somewhere over here, and I can show you the extent using a dotted line. So there you go. This is the view point from one of the sides. I hope you understand, and I have already shown you the picture of the equatorial plane, so that might be clear for you now. Alright, so now take some point, some arbitrary point which is not your origin. Okay, origin is also a point, or the dipole center is also a point on the equatorial plane, but I don't want to I'm not very interested in that particular point because we have already evaluated it. And let me show you in reference to rest of the system how the electric field at O looks like this. This is the electric field at O. Okay, let it be there. Now consider some arbitrary point P on the equatorial plane. I need to measure the electric field, the total electric field at P. What would it be? So before mentioning the magnitude of the electric field, let me just try to evaluate the direction of electric field over there. So for that, I can treat the system as if two charges consisting of two different point charges located at two different positions, and P is some point in space. So the net electric field at P, the total electric field at P, will be the vector sum of the electric field due to the positive charge and the electric field due to the negative charge. So this will be the representative of the equation or the vector at P. Since I had already told you the point P is an equatorial point, the distance it is from either charges will be the same. That means if you measure the distance of the point P from the positive charge, or whether you measure the distance of the same charge from the minus Q, will be the same. So as per our previous label, this distance was R plus and this distance was R minus. Okay, R plus and R minus. So these were the two distances. Very good. And the point itself should be represented using the vector from the origin. So this point P lies on the equatorial plane and is at some distance R from the origin O, just as in previous case. One thing we already know about the system is that this distance of these charges were A. Let me get rid of this electric field for a short while. So this distance here is A and this distance over here is also A. Fine. Since we have mentioned and drawn all the distances involved, so it's time for us to evaluate the electric field, the direction of electric field. Now, if no other charge existed in this region, I mean even in the presence of any other charge, the superposition principle states that the electric field due to individual charge is unaffected. That means the charge plus Q will have an electric field at P and its direction will be along its radius. Since it's positive, it should be radially outwards for charge plus Q. Now what about the charge minus Q? What will be the direction of the electric field due to minus Q? At P, the direction of the electric field due to minus Q will be towards the minus Q charge, which is radially inward for the minus Q. So we get the two charges, which is electric field due to the two charges. One is E plus and the other one is vector E minus. Okay, very good. So we have two different vectors. Let me label the charge minus Q using red and also label the corresponding vector red. Okay, so what is the sum of two vectors? In this case, we have two vectors, E plus in that direction and E minus in that direction, both acting at the same point P, which means their sum will be some can be taken using the parallelogram law of effect addition. So according to parallelogram law of effect addition, this sum should be somewhat like, it should run like this, and there must be, I must complete a parallelogram out of these two sides, and as you can see, you end up making some figure like this, and the diagonal of that figure will represent the total electric field E. Okay, so from the figure it is obvious that the direction of E is in the minus I cap direction, which is, it is parallel, it is anti-parallel to the dipole moment. But we can prove that too. How can we prove it? Now the first result we know about the system is that the distance r plus is equal to the distance r minus. Okay, because it's an equatorial point and the distance from each charges must be the same. So this is a known fact. So if that is the case, as you can see, the triangle plus q p o and minus q p o are congruent because they have other two sides also which are equal. So three sides equal means the triangles must be congruent. So they are congruent. Okay, why would I even want to have that result here? And that the result, I mean, yeah, we can have that result because we can make use of it to establish exactly the fact that E is pointed exactly in the I cap direction. So if this angle is, say, theta, and then we need to know what angle this will be, the angle between E plus vector and E minus vector. So I need to know the angle between E plus vector and the E minus vector. If this is theta, so in accordance to some rule in mathematics which states that the angle, and also since these two triangles were congruent, this angle will also be theta. That means the sum of the interior angle should be equal to the exterior angle, and the exterior angle is nothing but the angle that we were talking about. Let me call it theta prime. So the angle, this much angle, the angle between the green arrow and the red arrow is theta prime. I don't mind the minus, sorry, the blue arrow in between. Okay, don't mind the blue arrow in between. Okay, if you want, I can get rid of it too. So now you can see there is the theta prime is the angle between E plus and E minus. But E plus and E minus have the same magnitude. Why is that the case? Because the charges involved have the same magnitude, and also the point P is at the same distance from these two charges. So the value of electric fields E plus and E minus due to the point charges will be same. The magnitudes will be same. That means the length of the arrow will be same, which results in a sum that will bisect the angle theta prime. So now you know why I am doing that. So I have stated a few facts, one of which was that the angle theta plus theta adds up to theta prime, which means theta 2 theta becomes theta prime. So since the vector E bisects the angle theta prime, the angle on either sides, that is here and here, these two angles will be exactly half of theta prime. So from here it is clear that what is half of theta prime? Half of theta prime is indeed angle theta. So what do you understand from that? You understand only one thing, that the vector E is parallel to the I cap direction, or it is parallel to the x-axis in this coordinate system, in the defined coordinate system. See, over here it is a minus, so it is E minus, don't forget that. So let me get rid of theta prime. You know now what theta prime is. So let me label the half angle. This is theta, and this will also be theta. Now you know, because the vector E is bisecting the angle theta prime. Now you have the following situation. You have a vector like that, pointing like that, another vector pointing like this, and they have their sum in this direction. This is, say, E plus, and this was E minus, and this angle is theta, you know now, and this angle is also theta, you know. So what is the magnitude of E in this case? If you have a prior knowledge of vector algebra, this is easily evaluated as the vector E. The magnitude of vector E is nothing but, let me just move this a little bit to the side. So value of this vector, the magnitude of this sum vector, is equal to magnitude of E plus cos theta, which is the angle between E plus and E, plus magnitude of the vector E minus cos theta, which is the angle between E and E minus. One fact we have forgot to mention, or at least write it down, was that the magnitude of E plus was equal to the magnitude of E minus. I can call it E0 for the time being, because I can easily evaluate the value of E0. How can you evaluate the value of E0? See, taking either one of the charges, E0 will look like 1 by 4 pi epsilon 0, and you can call R plus and R minus as some R prime. Okay, R prime would be a good equivalent representative, because they are same, so I can call them R prime. So E0 will be 1 by 4 pi epsilon 0 times Q divided by R prime squared. So E0 is known. The only number here which disgusts us is the R prime, because I think we don't have to go on ahead to completely measure this distance R prime from the plane. So instead we can replace the R prime in terms of R and A. R and A. How? From this triangle P plus QO, you have the triangle P plus QO. You can see that the so-called R prime distance, the charge distance from the charge, one of the charges, is actually the hypotenuse of that triangle, since this is a 90-degree. So what will be R prime? What will be R prime? R prime will be the square of the sum of the squares of the base and the altitude. So A is the base, R is the altitude, R prime is the hypotenuse. So we end up in the following equation, which says that R prime squared is equal to R squared plus A squared. So I can now replace R prime in the equation for the magnitude of the electric field. Very good. So instead of E magnitude of E plus or magnitude of E minus, I can write it together as E0 cos theta plus E0 cos theta. Oh, that seems to be two terms, two same terms. So You are adding them, which means it is 2 times E0 cos theta. Very good. You know what is E0 is. Now what is cos theta? How can you determine cos theta? Again we go back to the triangle PQ prime O. Sorry, PQ plus or plus QO. P plus QO. Can you see the triangle? It's over here. Okay, it's over there. From this triangle, you see the angle placed there. From that figure, theta can be cos theta can be found out as adjacent side divided by the hypotenuse r prime. So adjacent side is a and hypotenuse is r prime, which is r square plus a square the whole root. So cos theta will also get an easy replacement, which is cos theta is equal to a, which is the adjacent side, divided by r prime, which was the hypotenuse. So instead of r prime, we have a divided by whole root of r square plus a square. So there you go. Now we have replaced E0. We have a replacement for E0. We have a replacement for cos theta. And then we want to do is combine these two together and find out the resultant. So let us just do that right now. We know the magnitude of the resultant vector, resultant electric field, was found out to be 2 times sum E0 cos theta. So now just replace each and every term. 2 into E0 was 1 by 4 pi epsilon 0 times q by, it was r prime square. Now we have replaced r prime squared as r square plus a squared, again into what was cos theta. So cos theta was a divided by the square root of, again, r square plus a square. All right, there you go. So what can we do to simplify this equation? See, the denominator seems to be a bit fuzzy. So let's just combine them, because there is a rule in mathematics. If you have two base raised to different powers and multiplied, that is, you have same base a raised to m and some other a raised to n, and then you multiply it, the result seems to be a very nice one, because all you need to do is put the base only one times and add the powers. So this is also another rule of powers or exponents. You can make use of this, but it is unclear in this case. See, m and n can be any values. They can be integers, they can be real numbers, they can be just a fraction, no problem. So how can you apply this into this? It's very clear from this. In the denominator you have, let me just put all the terms in the numerator together. You have 2, you have a, you have q. You have got something very interesting over here. Okay, we will replace that a little bit later. 2aq, you know what it is. So 1 by 4 pi epsilon 0, let it stay there. So in the denominator you have the base r square plus a square the whole raised to 1. Okay, because there is only you are not raising it with anything, so you can write it as a raised to 1. Now you have the root of r square plus a square. See, the root power can equally be represented using raised to 1 over 2. So this is what square root looks in numbers, in terms of numbers. Okay, now you have the same base. The base is r square plus a square. You can write it only one times, and the power m is 1 and the power n is 1 by 2. So using the rule, I can just completely take it off and have r square plus a square the whole raised to 1 plus 1 by 2, which is doing after a little bit of mathematics, I will know that is 3 by 2. So you get is over here you have raised to 3 by 2. Now that seems to be a very complicated power, but anyhow, meanwhile that will do the job. So now you got the total expression for the electric field at an equatorial point. Sorry for the break, but yeah. Let us see what that total expression looks like. So the total expression looks like this. Magnitude of the electric field, total electric field E is equal to 2 times AQ divided by 4 pi epsilon 0 times R square plus A square the whole raised to 3 by 2. So there you go. So that's your entire expression for electric field. Now let me just put this under a square bracket, not a square bracket but a square box. So there you go, you have your electric field. So if you want to write this in terms of vector notation, I can do that too. One thing you know is that the total electric field was in the I cap direction, not in the minus I cap. Sorry about that. It is in the I cap direction. So it's already a well-known thing that the total electric field E is in the I cap direction. So vector E can be represented as, so I'm going to replace 2AQ. No, let it stay there for a while. Okay, let it stay there for a while, because I'm going to convert it into vector. So 2AQ, you have 2AQ, and you have your I cap. Now you need to put I cap. Let me use some other symbol, color. Okay, 2AQ I cap, the whole divided by the terms in the denominator, which is 4 pi epsilon 0 times R square plus A square the whole raised to 3 by 2. Now you got your vector equation. But the problem with the vector equation, no, there are no problems involved actually. One thing you need to remember is that the vector, the dipole moment vector P was equal to some minus 2AQ I cap. So the term in the numerator lacks a minus. So to compensate for that, see, I can replace 2AQ from here itself. I can replace 2AQ I cap as minus P, because I'm just bringing the minus onto the other side. So which means a dipole moment pointed in opposite direction. So now you can replace 2AQ I cap as minus vector P. So there you go, you have your complete equation, which is also in its vector form. This is the magnitude. So if you want to replace 2AQ over here on top, you can do that too. Just write the magnitude. 2AQ is the magnitude of the dipole moment, so you can write P here, or you can just do this, put this bracket and then put the vector P inside, which means its magnitude. So let me write that 2 here is equal to 2AQ. Don't forget this. So this is the equation of electric field on an equatorial point, at an arbitrary equatorial point. Okay, so at an arbitrary equatorial point. So that's your expression. You can use this as your vector equation, and you can use this as your magnitude equation. In some textbooks, they easily remove these brackets just to show that vector magnitudes can be easily represented without arrow. without the symbols without the arrow represents the magnitude, whereas the vectors, to write the vectors you need to put the arrow on top. That's all. When you invoke the vector part, you know that the electric field on the equatorial, any point on the equatorial plane, will be opposite to the dipole moment vector. This is what the minus sign over here stands for. So just as in previous case, we may also apply the approximation here for a bit more of easier equation, the approximation. So we are going to do the approximation. So the approximation here is also exactly similar to what we did in the axial case. That is, we assume that the dipole is very small. Either we assume that it is very small, or we assume that we are viewing the dipole from a very far away point. Okay, suppose that equatorial point was here, and we are viewing it from like miles across. See, miles across is bit too of an over exaggeration, but still it will work for the names. For this case, this will work. But anyhow, if you are assuming a very realistic dipole, it has no significant effect miles across. So you get the point, right? I'm just not trying to assert the concept there. It's just that R is very large as in comparison to the A. So here also your point P is very far away from the dipole. So in this case, what happens? Again, in this case, it's very easy. Let me just write down the expression first. Let me just indicate the expression. So this was our expression. So by applying this approximation, now you have learned how to apply approximation in the case of additions. What you do is just neglect the smaller term, and you end up with this same expression which involves all the terms in the numerator, like there will be P, and there will be 4 pi epsilon 0, 4 pi epsilon 0. So what is gone is the A, and you remain with an R square, the whole raised to some 3 by 2. So you have R square, the whole raised to 3 by 2, which is nothing but will have to multiply the power 2 times 3 by 2, which will give you 2 gets cancelled. You only remain with the power 3. So this ends up with an R cube. So let me just get a thicker pen color, yeah, and you have here is a cube. That's all, and there you go. That's it. That's the approximation. That's how good the approximation here is. So you have electric field at the axial point after approximation, not the axial point, sorry, the equatorial point, gives you an expression again which looks like very similar to the previous case, but there is a slight difference. Can you point out now what's the difference between the approximate expression in the axial as well as in the equatorial cases? You can pause for a few seconds and then say it. If you still don't get it, let me remind you there was a 2 in the case of the axial point. So that's one difference. But here also your electric field E becomes inversely proportional to the cube of the distance from the dipole. So in both these cases, this is going to be exactly the same. The dependence will be exactly similar, but the only difference is that on the equatorial point at a distance r, at a far away distance r on the equatorial point, if the electric field is E, and some point r distant away in the axial point, you will have an electric field which will be 2 times this E. So there is more electric field on the axial point than on the equatorial point. I mean, the strength of the electric field is 2 times. These are all for approximate cases. When it comes to very nearby cases, you will have to use the exact expression to understand how they behave. So there you go. You have your 2 expressions derived, and that's good for your exams. Now, let us move on to the last topic of this video. The last topic of the video is electric dipoles in uniform external electric field. So I have only mentioned field, but it actually means the electric field in this context, so don't forget that. A uniform field can be represented using field lines, okay, electric field lines. So in any region, if you have an uniform electric field, the uniform electric field will look something like this. If you represent uniform field using field lines, they will be nothing but parallel lines passing through that region. So the direction of the arrow will represent the global direction of the electric field in that region, which in this case will be from your left to right. I think I can just copy and I can compress it. I don't want to compress it too much, but to make it a bit more thicker, I can copy this image and then paste it over here. I don't want to go over that side. Please, can I scroll back? Yep. All right, so we have that. So this is what a uniform field will look like if you represent it using electric field lines. So this is the region. This region between these lines are actually the electric field. So everywhere, so what do you mean by electric field which is a uniform one? It means that any point here, any point in between, wherever you go, wherever it be, okay, wherever there are infinite number of points in this region, you know that. So practically it is impossible to represent all the points, but at any point, at any arbitrary point, the electric field will all be pointed in the same direction, like this, like this, like this, like this, and maybe over here, and like this over here, and like this over here. The thing is, the value of the electric field will also, the magnitude of field in the whole region will also be the same. It will all be pointed in the same direction, and it will all be having the same magnitude, which means your electric field is uniform. That is what it means. So at any point, magnitude will remain a constant. So let me just get rid of all these representations. That will actually, it's better. Oh my gosh. Okay, go away, go away, go away, go away. So there you go. I have got rid of all the smaller points, and now we have our constant uniform field or uniform field. So this is an external field, which means this electric field is being produced by some source charge system. I don't know, it can be anything. It's and there is some positive, this is on this side we have positive charge system, and this side maybe there is a negative source charge system. So this is like produced by some external agency. We don't care about them right now. All we care about in this situation is an electric dipole. So what was an electric dipole? You had an electric dipole. Your electric dipole was a positive charge and some negative charge separated by a finite distance. Maybe I can use this color, separated by some finite distance like this. Let me use okay, whoops, there you go. So this is your electric dipole, and they are separated by some tiny distance. Okay, let's let the distance be some 2a. Okay, and by the way, this was your minus q and this was your plus q. So what will happen if I put such a dipole, such an electric dipole, in the presence of an external electric field? What is going to happen? So that's a question. How will it behave? Now this arrow actually indicates the direction, also indicates the direction in which your dipole moment is, because dipole moment is directed from minus q to plus q. So remember that. Now it is oriented. So now I can talk about the orientation of this electric dipole in this electric field, right? See, the dipole moment is actually oriented in certain way with respect to the external electric field. So the external electric field, which is obviously in some direction like this, okay, it's in some direction like that. Maybe I can okay, you have your external electric field looking that way, and you have your dipole moment vector looking that way, and the angle, as you can see, between them is some theta. All right. What will happen to this plus q charge in the presence of this external electric field? The positive charge in the presence of an external electric field will experience some force, right? Because at this point, at this particular point, there is a value for electric field, and I call it E. As I mentioned, everywhere it is E because it was a uniform field. So at this point, if the value is E and you have placed some charge plus q, what should the direction and the magnitude of electric force at that point be? So at this point, the force will be F is equal to plus q E. If you represent it vectorially, you may use that plus over there, and that direction of force will be in the direction of the electric field. So this is the force experienced by the plus q charge, and this will be the direction. Now what about the minus charge? The negative charge also experiences a force because it is in the presence of electric field E. So the force at this particular point will be F is equal to minus q times E. Only use the minus if you are representing everything vectorially. So the direction of that force will be opposite to what it is for the case of positive charge. So this will be the force on the negative charge. This is the force on the positive charge. But one thing is clear, that these two forces have the same magnitude. All right. So suppose, imagine that your dipole is some sort of a rigid rod, which means these two points cannot move away from one another. Okay, if they cannot move away from one another and they are stuck onto each other, so they act like a rigid rod, right? So rigid rod, their behavior is now like a rigid body, a rigid rod. A rigid rod is actually a two-dimensional or a one-dimensional rigid body. So this rigid body has forces acting on it on two ends of the body at certain angle. The question will be, what will be the physical effect of such a pair of forces acting on a rigid body at two ends? The answer is the body will experience a torque. And what is the effect of torque? The torque tries to rotate the system. So that is indeed what happens in this case. due to these forces, a torque comes into play, and the torque tries to rotate the dipole in this manner. So this will be the direction in which the dipole, the electric dipole, will rotate. Now we need to find out the expression for torque, because evaluating the torque will give us certain idea about the energy of the system. So let us go ahead and evaluate the expression for torque. So let us see what would the expression for torque on an electric dipole in the presence of an external uniform field look like. So for that, let me just bring back the diagram. So there you have the diagram, and here over here we can draw the dipole moment vector. Let me just replace it with our standard color. So there you have the electric dipole, and with represented using its dipole moment vector. Now labeling the charges, this was your minus q and this was your plus q. All right, now view it from some external point O. So if when you are viewing it from some external point O, I can mark the distance over here. I have the distance, the position, not the distance, but instead the position to the minus q charge. Let me call it r minus, vector r minus, because this is, be careful, I'm not just representing the distance, but instead I'm representing the position. Now what about the positive charge? Similarly, you can also label a position for the positive charge. There you go, and I can call it r vector r minus, no, vector r plus. So you have vector r minus, which gives you the position of minus q, and vector r plus, which will give you the position of plus q. All right, so the forces involved, let us go ahead and check the forces involved. The force that was acting on plus q was like this, and let me call it f. Okay, f plus. If you want to call it f plus, it's good, because that would you would be able to distinguish it. And the force acting on negative charge was in this direction, and I can call it f vector f minus. See, the thing is, f plus or your f minus, both were equal in magnitude but opposite in direction. So I can just call f plus is equal to minus f minus. So I can replace their magnitudes. They have the same magnitude, right? They have the same magnitude, which is equal to q e. See, in terms of magnitude, okay, in terms of magnitude, this is q e. Okay, in terms of vector, this will look like f plus is in the direction of electric field. So I can write f plus as q e, and I can write f minus as minus q e. So these are a few things you need to learn before you write the expression for the torque. So now what is torque? The torque acting on this system is actually the sum of all the moments of forces on the system. So that is you have to find the moment of each forces. So what is a moment of force? I will mention that right now. So the torque on the system will be equal to sum of moments of forces acting on the body. So what is a moment of force? Is defined as the cross product of the position vector with the force vector. So this is what the moment of force. A moment of force is the cross product between the position vector and the force at this position. Okay, so how many moments of force are there? See, moment I can call mu1 as the first moment of force, which is nothing but the position r1 times the force at r1. The force at r1 was actually there is no position such as r1. It's actually we should instead call it the moment of force at the negative charge is vector r minus times the force, which is F minus. That was the force at r minus, and this is vector r minus. Instead of F minus, I can call it minus q times vector E, which we had seen earlier. Now what is the moment of force at the positive charge? At the positive charge, the moment of force is r plus, that is the position of the positive charge, times the force at that position. It is F plus. So this will look like r plus times plus q into the electric field, because it was in the direction of electric field. So you got it. You have the two moments of force. So according to the definition, torque represented using torque is represented using a Greek letter called tau. So remember this. Okay, so this will be the tau that I am going to write. So this is our tau, just like in towel. Okay, anyways, that's not very close to it. So tau, and also it's a vector, so don't forget to put an arrow. So tau is a vector, and that will be equal to the sum of the total moments of force, which is in this case it's mu minus, vector mu minus plus vector mu plus, and we had already evaluated for these individual terms, and they were r vector r minus times minus q vector E. There's a cross over here. There's a cross. Oh, I forgot to put a cross over here. Oh my goodness, that's something I forgot already. So there is a cross over here as well. Please forgive me. Please forgive me for that, because see, we had already had that in definition, but I forgot. See, this is a vector product here. Okay, this is a vector product. So don't think that it is any usual one. It's you're taking the product between two vectors, and that two vectors after undergoing this operation yield a vector itself. That's why this was a vector, unlike in the case of a dot product, which yields a scalar. But in this case, when you multiply a vector using two vectors using a cross product or the vector product, you will end up getting a vector. Okay, fine. So that is there, and then what was mu plus? It was vector r times q. Oh, it's a plus over here. Q E. All right, so I think the space is already jammed up, so let me just use a new page. So I have rewritten the expression for torque. From this I have a few manipulations to make. The few manipulations are I can pull out the Q and the E to left side. See, this is a cross product, so you should be very careful on which side you pull out the common terms. Okay, I will explain that some other day. So since these two terms QE are common in each case, and also they are on the left side of the product, they should be pulled out. Sorry, they are on the right side of the product, so they should be pulled out to the right side. This is something that you must always follow in the case of a cross product, so which will result in the following expression. So you have got your minus, you have got your QE outside, the vector QE is outside, and inside the bracket you have minus R minus plus R. Oh, there's a plus here. Why do I keep writing it minus? I don't know. Maybe some precision mistakes, right? Okay, then correcting this part is actually correct, but just rearranging the terms, you get this. So there is one more freedom in this cross product, that is Q is a scalar, and I can move scalar throughout the expression wherever I like, because scalars only tend to scale the vectors, so they can be pulled out to the front like this, and so you have this is the difference vector. I can call it vector D, and you have this electric field E, and in between them we have the cross product, and in front of it we have Q. So what was Q times the difference vector? Q times the difference vector, or the dipole length vector, is indeed the electric dipole moment, which is P. So QD together makes the vector P, and all we have is cross E, or I can use a blue color instead. So E. So this is what the expression for torque is. This is how you derive the expression for torque for an electric dipole in the presence of a uniform field E, and the dipole moment has a electric dipole moment P. The expression can be further evaluated for its magnitude. That is, you had the expression torque is equal to the dipole moment cross the electric field. So it is a cross product between the dipole moment and the electric field. So what will be the magnitude of the torque? The magnitude of the torque tau should be equal to magnitude of the dipole moment times magnitude of the electric field times cosine. It's not cosine, it's sine. It's sine of the angle between the two vectors. I call it theta. So if your electric field E is pointed in this direction, you have a uniform electric field pointing in that direction, and if you have your dipole moment in this electric field pointing in some other direction like that, and suppose there is an angle between them, and let it be theta, then the torque acting on the dipole moment will be tau is equal to Pe sine theta. magnitude wise. So there you go, you have all the information, basic information on about an electric dipole, including the expressions. So I think this much is enough for you as part of your derivations for the NCERT. Yeah, I mean, I can do a further analysis on this. See, since this gives the magnitude of torque, I can define three things. One is when you keep the dipole moment or the electric dipole with its dipole moment parallel to the electric field, the angle will be 0 degree, which means which results in a sin theta value of 0. Thus the torque acting on the electric dipole will also be 0. Now we have second condition or a second situation in which your electric dipole's dipole moment is perpendicular to the electric field. So in this case, the angle involved is 90 degree. So you have a theta value of 90 degree and a sin 90 value which gives you 1 in this case. If sin theta is 1, then the expression will have its maximum value, which means you will have a maximum torque acting on the dipole, and that value is equal to P times E. And you have this third case in which your dipole moment could be pointed exactly in the opposite direction with respect to your electric field, which means their angle will be 180 degree. And 180 degree, an angle theta of 180 degree also results in a similar situation, which is sin 180 is 0, which is similar to first case, and the torque you get is 0, but there is a difference here. The difference is that if you slightly perturb your electric dipole either to the left or to the right, the issue is that the angle will become not 180. The angle will become lesser than 180. So once the angle gets lesser than 180, the torque becomes non-zero and it will twist it back to its initial position, which is not the initial position, to a state of equilibrium. That means it's like trying to balance. If you are trying to put a dipole at 180 degree, it's like trying to balance a pen on a table. When you put a pen on a table vertically, there is only a particular point at which it will balance, but if the angle is slightly different from that, what will happen? The pen will fall down. Similarly, the electric dipole will also fall back to the first situation, where the situation is called, when the angle is 0, the situation is called stable equilibrium. And in the 180 degree case, it seems to be the torque is 0, but it's not under proper stable equilibrium, but it's under unstable equilibrium. So you have unstable equilibrium. But what about in this case? In this case, it is not at all under any equilibrium. It is at the maximum torque possible, so it is non-equilibrium position. So any angle between 0 and 180 is a non-equilibrium situation, but this is the most unstable or the maximum torque position. So this is an unstable position at theta equal to 90 degree. So that's it, guys. That's all for today's classes. We will be discussing about the energy of electric dipoles in chapter number 2. So thank you kindly, and that's the end of this.